Good. Like those, again, it's when you're listing off all the possible outcomes of events, usually consecutive, like one after the other, but they could be simultaneous if it doesn't matter in the order. There might be some examples here. Not really. No. Okay. So it's, let's say I'm interested in, let's say I have a bag. Let's take an example here. I'm going to make my own example. A bag of marbles. Okay. And in there's 7 green ones and 13 red ones. Not very original, but there you go. I pick 2 balls of marbles, sorry, just to be quite specific here. 2 marbles without replacement. You'll hear this without replacement or with replacement. It means, do I put the first one back or do I not? Because that can change the outcomes. And then I can say, find the probability that I get 2 red ones. Or find the probability that I get at least 1 green. Okay, so what I could do is draw a quick tree diagram. Your Venn diagram won't work in this one because what's happening is the outcomes are changing depending on what happens first. So what do I mean by that? I pull out one of the marbles and either it comes out green or it comes out red. And what you do is you fill in the probabilities. So the probability that is green is 7 out of 20 because there's 20 in total, and red is 13 out of 20. Fine. So you make kind of this kind of split like this for every decision you got to make. Now, if you pick the green one, you will again have a chance of getting a green one or a red one. The probability of you getting a green one, though, in this case, has changed to 6 out of 19 because there's only 19 balls left and there's only 6 green ones. There are 13 red ones left, but only 19 left in total. These things, by the way, these splits have got to add up to 1. Otherwise, you're doing it wrong. If you pick a red one, you can get a green or a red again. Probability of getting a green one, though, is 7 out of 19 because there are still 7 green ones left. Probability of getting a red one, though, is 13 out of, no, 12 out of 19. And again, this adds that up to 1. Okay? And then if I want to answer my question, find the probability that I get 2 red ones. Well, what I do is I kind of look at all the paths that lead to success. So 2 reds is only this path that works. And so I need a red and a red. So when I say kind of like red and red, I multiply. So you multiply along the paths. So the probability of 2 reds is equal to 13 out of 20 times 12 out of 19. And that'll equal to something. That's it. A. B, the probability that at least 1 green. There's a fast way of writing it. Green is greater than 1. How I do that is I look at all the possible paths that gives me at least 1 green. So that's this one, or this one, or this one. So those 3 paths. So one way I can do it, and I notice I said one way because there's going to be another way, is you can go 7 out of 20 times 6 out of 19 plus, and you add up the different paths because I can go green, green, or I can go green, red, or I can go red, green. What happened? And I'll let you calculate that. I'm just too lazy. Or what I could do is, if it's easier, you can just say 1, because that's all the possible outcomes, minus the outcomes you don't want, which is green equals 0, or in other words, in this case, 2 red ones. So in this case, that would be 1 minus the probability of 2 reds, which you already calculated in A, so you could just do a very quick calculation on an exam. And I'll let you calculate that. So that's what the tree diagram looks like. A couple of pointers here. If you do events over and over again, these branches, like, so if I do something 3 times, 4 times, 5 times, you'll just keep splitting off on events, right? It'll just keep splitting and splitting and splitting. It gets pretty big and bulky. There are some nice formulas for patterns that you can develop in this. Could be a good IA, but it's not part of this course to really develop that too much, except in the condition that what if you're repeating things over and over again that are the same? Like, for example, if you have a 6-sided die, what's the probability of me rolling a 3? Well, it's 1 out of 6. Oops. 1 out of 6, right? There's only 1 3 on a 6-sided die, right? What if I do it twice? Well, what I could do is start doing a tree diagram if you want, because I can get the 3 or I can not get the 3. Don't do 1, 2, 3, 4, 5, 6. That's too many branches. Crazy. And the chance of this happening is this, and the chance of not getting a 3 is 5 out of 6. And if I do it again, the probabilities here of getting the 3 or not getting the 3 do not change. Sorry, that should go there. And that's called independent events, because they're not affecting each other. So if these things aren't changing, that means they don't affect each other. So 1 out of 6, 5 out of 6. So there is a pattern to this, and it's called the binomial pattern. But to keep things simply, there's a quick thing here you can do for simple situations. So I'll get back to the binomial theorem, but for this one, the 6-sided die, the probability of getting a 6 twice, or sorry, getting a 3 twice, so how would I write that? On 2 rolls, okay, would be 1 out of 6 times 1 out of 6, so it'd be squared. In fact, the probability of me getting a 3 5 times would be 1 out of 6 times 5 to the power of 5, because there's only one path and you keep multiplying by 1 out of 6. Sorry, this one. You would just keep going like that, on and on and on. So you see kind of an easy little pattern. I think you could figure that out. The thing is, with the binomial pattern, it's interesting. Ooh, I could do a whole lesson on this. Let me just give you a teaser. Let's say that instead of using a number like 3, let's say we let event A be the chances, the probability of A be the probability of getting a 3 on my example. So in other words, the probability of A is equal to 1 out of 6. Okay? Fine. Here's the neat thing. If you are interested, what happens? What happens along all these possible paths? Well, if I roll twice, here's what it looks like. Either A or not A happens, and you're going to do it twice. And you do this. A plus, what you're doing is like doing a binomial expansion. So it'll be A not A plus A not A plus not A squared. So it'll be 2A not A plus not A squared. Like that. And so and that's squared. So the probability of getting A twice is 2 A's would be equal to A squared. So it would be equal to 1 out of 6 squared. But the probability of getting A and then not A is 2 times the probability of getting an A times the probability of not getting an A. I'm using this. I'm using this. And the probability of getting not A and then not A, if you want, maybe that's a nicer way, AA, not A and not A, I'm going to use this. So it'll be 5 out of 6 times 5 out of 6. And if you add all those up, you'll get 1. So if you add all of these up, you get 1. Because you have to, because those are all the possible outcomes. So this is a binomial expansion. In fact, if I roll 3 times, it's the same deal. It's going to be A, not A to the power of 3, and you just expand that. And if I expand it quickly, it's this cubed plus 3A, 2 A's, and 1 not A, plus 3A, not A possibilities, plus not A cubed. So it'd be 1 out of 6 cubed to get 3 A's. It would be 3 1 out of 6's squared, 5 out of 6. This would be the probability of getting 2 A's and not an A. This would be the probability of getting A and then not A twice in any order. And this would be probability of getting it not A 3 times. And that would, I guarantee, add up to 1. In fact, this is 1 out of 6. This is 5 out of 6. That becomes 1. 1 to the power of 3 is 1. Same deal here if I expand that. It's really, really interesting. May not seem to you, but it is very interesting. I'm going to do a quick question and then move on. Let's pick this one. It looks short. Chevy player plays a game in which he throws a pair of dice numbered 1, 2, 3, 4, 5, 6, 24 times. Find the probability that she throws at least one double six. Okay, so they're keeping it simple. This one's fairly easy because the probability of at least one double six. So, the probability that this is at least one, okay, is a tough one to calculate because there's a lot of possible ways you can do that if you do it 24 times. But it's much easier to say, to count the situations you don't want. So, no 6. No double 6. Okay, why is that easier? There's only one way you can that she throws at least one double 6. Throws a pair of fair, because okay, what's the probability of getting a double 6 if you roll throws a pair of fair die? The chances of that, there are 36 possible outcomes, and there's only one way you can get 2 6s. So again, you can make one of these little diagrams. 1, 2, 3, 4, 5, 6. That's one die. And the other one is 1, 2, 3, 4, 5, 6. You can make one of these, but boy, that would take a long time. Bit of a waste of time, really. But there are 36 outcomes there. Okay? There are 36 possibilities in here. You can get a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, etc., etc., etc. But there's only one, and only one double 6 out of all those. So 1 out of 36. And so if you do this 24 times, never getting that, the chance of not getting a double 6 is therefore 35 out of 36. And you repeat it 24 times. So this would be your probability. So what's the probability of never getting a double 6 if you do it 24 times? See, this is good for gambling. it would be 1 minus bracket 35 divided by 36, close bracket, raise to the power of 24, boom, and it is, interestingly enough, 0.49. 1. So 49% chance. So basically, half the time, you'll never roll a double 6 if you roll 24 times. Yeah, it's a bit surprising to me, but that's what statistics is all about. Is there more? Yes, but I'm going to stop here.